Okay, today's we'll study 2 and 3D motion. So last chapter we studied motion in 1 dimensions, and so in 3D we're going to combine 3 1D motions into a single 3D motion. So for instance, here's a general 3D trajectory. Well, this is a 2D trajectory. So let's see. Oh, I don't have a 3D trajectory. Okay, here, okay. So here's a particle, a plane, bird, or whatever that's flying around. Okay, and this motion can be parameterized in terms of the time. So this is where the bird is at 0 seconds, 1 second, 2 seconds, and so on. Okay. So the motion is completely described when you are given these 3 functions. When you're given x as a function of time, y as a function of time, and z as a function of time. So to describe this completely, to describe this motion completely, you have to give me those 3 functions, x, y, and z. Okay? So let's do an example. We'll all right, so what we are interested in is this general 3D motion. Okay. And the position vector of this guy is the position at a given time, RT. So the position vector is a vector pointing from the origin to your location at a given time. Okay? And that, okay. So to describe this motion, what do you have to do? You have to give me these 3 functions. The x coordinate as a function of time, the y coordinate as a function of time, and the z coordinate as a function of time. Okay. And let's make up some examples. Okay. So what I'll describe to you is what I'll write an equation for is not this motion. I mean, this could be any general motion. I'll write to you a motion for a spiral object moving in a spiral, and it's moving upward in an upward spiral. Okay, so I'll give you an equation for that. R cosine omega t I plus R sine omega t j plus 5 t plus 7 k. Okay, so what this is this is an object going in a spiral with an upward velocity of 5 meters per second. Okay, so that's the velocity in the z direction is 5 meters per second. It starts off at 7 meters. Okay? You don't have to worry about all of that. Here is a general motion, a 3D motion. Okay. All right. So where are we? Okay. So we are interested in describing this motion. Okay. And here's a complete description of the motion when you give me these 3 functions. Okay. And now there'll be a couple of things we'll be interested in. What is the velocity of the object at any given time? And now you already know what is the velocity. The velocity is, it's the time derivative of the position vector. Okay. It's the time derivative of this guy. You guys understanding that? Okay. So this would be the time derivative of that, plus the time derivative of that, plus the time derivative of that. Okay. So this would be dx by dt I plus dy by dt j plus dz by dt k. Okay, that's the velocity of the object. And this is the x component of the velocity. This is the y component of the velocity. This is the z component of the velocity. Just like you've seen for a vector, this is the ax, ay, az. Okay, the x component of the velocity is given by that. The y component of the velocity is given by that. The z component of the velocity is given by that. Okay? Now, what is this velocity? It's a vector. It has a magnitude and direction. Okay? Now we can tell you the direction. Okay, so the velocity vector will always be tangent to the trajectory. Okay? Its length will of course depend on how fast you're going at that moment, and that information will be contained in the functions. Okay. You guys understanding this? Okay. Right, so let's do this. Let's calculate the velocity for this function. Okay. So velocity okay, so who can help me out with the derivative of this guy? That is the x function, x coordinate as a function of time. What is the derivative of that? R is a constant. What is the derivative of cosine? Very good, negative sign. So it's minus R, and omega is a constant, sine omega t I. Okay. So what we have said is d by dt of R cosine omega t is, that's a constant. So from the chain rule, we get that. Okay. All right. The next one. What is the derivative of R sine omega t? Yeah, right. So R cosine omega t, and then you get an omega from the chain rule. Cosine omega t j. And the z component of the velocity? I'm sorry? Well, just 5. Okay. And like I said, the z component of the velocity is 5 meters per second. Okay. Yep.
Omega is a constant?
Omega is a constant. Okay. So remember, this motion I said is a spiral motion, and omega is the angular velocity. Okay. How many radians per second it's going around in a circle in the xy plane. That's what that is. Okay. All right. So now going back to our motion. So here's a 3D motion. There's the velocity. What is the other thing that you're interested in? Acceleration. And what is acceleration? Yeah, that's the time derivative of the velocity. Okay? And there's the velocity, and you take a time derivative of that, you get the second time derivative of the position. Okay? All right, so help me out with this thing. Okay, so there's the velocity. All right, so okay. Okay, so let's do the derivative of that. Can anybody help me out with the derivative of that? Very good. Negative. So derivative of this is cosine omega t, and then this is just not t, so when you take the derivative of that, you get an omega. So it'll be r omega squared. Okay. All right. The next term. I'm sorry? Derivative of sine is cosine. Yeah, sine. Yep. Mm-hmm. And then next? 0, okay. That's it. Okay, you're all done. You want to describe a three-dimensional motion, you give me these three functions. Okay. All right, so we'll RT equal to so you want to describe a general motion, you give me a general 3D motion, give me these three functions, and then I know how to calculate what I need to know. Okay. This is a complete description of the motion. You're giving me three functions. I can calculate the velocity and the acceleration. Okay. How many different kinds of motions are there? Infinite. As many functions as you can think of. If you're looking at 2D motion, what does that mean? A motion that's happening only in 2 dimensions in a plane, all you need is two functions. Okay? All right, so that's this chapter. Okay. So now let's go over the slides. The location of a particle is described by its position vector with respect to a coordinate system. Okay. So here is this object. Its position is the vector pointing from the origin to its location. Okay. That's its position vector with respect to this coordinate system. Its position vector with reference to a different coordinate system is that. Okay? All right, so for instance, all your addresses at home are given with respect to a coordinate system. In Daytona Beach, we refer the coordinate system from, maybe US1 and ISB. Okay. So, all right. So you give its position with respect to a coordinate system. And then when you're describing the motion, you're giving me these three functions. A complete description of the motion is given by its position as a function of time. Okay. So in 3 dimensions, you need 3 functions. In 5 dimensions, how many functions do you need? 5. Okay. All right. So if this is the trajectory you went on, and you were here now, and you were there a little while later, the displacement vector is a vector pointing straight from your initial position to your final position. Okay? So there's your displacement vector. The final position vector minus the initial position vector. Okay, so there's the final position vector, and there's the initial position vector. And this vector happens to be the difference of the two. And you can see that by bringing R2 is delta R plus R1. Okay, so if you bring this guy over that side, see R1 plus delta R is R2, which is what this equation is saying. Okay. So again, the displacement vector, again, it's a vector pointing from your initial position to your final position. We'll define average velocity, but we really are interested in instantaneous velocity, okay, because we know calculus. Okay. So average velocity is the displacement vector divided by the time over which that displacement happened. Okay, so for instance, if you went from here to there in 1 second, and your buddy went from here to there in 10 seconds, your velocity is greater, right? Your average velocity is greater. So smaller the time interval, greater your average velocity. Okay? Even though your average velocity will point in the same direction, the magnitude is different depending on the time over which that distance is covered. Okay. Instantaneous velocity is the average velocity in the limit delta t going to 0. And that's the time derivative of the position vector. Okay? And that velocity vector is always tangent to the trajectory. The magnitude of the velocity is your speed, and that depends on how fast you're covering an infinitesimal distance. Okay. All right. But the direction of the velocity vector will always be tangent to the path. Yeah. All right, so the velocity vector is given by dx by dt, dy by I plus dy by dt, j plus dz by dt. Okay. All right, so now that you know this technology, you can do any motion. You can do 1 dimension, 2 dimensions, 3 dimension, n-dimensional motion. Okay, it's the same technology. The magnitude of the instantaneous velocity. What do you mean by the magnitude of the instantaneous velocity? The magnitude of this vector, okay, which gives you the length of this vector, is your speed at that instant. Okay, so that's what your speedometer tells you in your car. That's your speed at that instant. Okay. So the direction is tangent to the path. Acceleration. When are you accelerating?
Whenever changing direction, there's velocity.
What's that? Okay. So all questions can be answered by looking at equations. Here's the definition of acceleration. What is the acceleration defined? Time rate of change of velocity. If your velocity is constant in time, then you're not accelerating. If your velocity is changing with time, then you're accelerating. Okay? Velocity is a vector, and like our friend said, to change a vector, what do you have to do? You can change either the magnitude, direction, or both. Okay? So anytime your velocity changes, you're accelerating. And that's what this is saying. See, over a time period, the velocity changed. If the velocity does not change, this would be 0, v2 would be equal to v1, that would not change, and your acceleration would be 0. Okay? So you are accelerating anytime your velocity changes. So for instance, if you're going on a curved path, see, the velocity is tangent to the path. Even if your speed is not changing, you see the direction of the velocity vector is changing, so you're accelerating. Now, on a straight path, if your speed doesn't change, the direction is not changing and you're not accelerating. Okay? All right, so you're accelerating anytime your velocity changes, and that's how average acceleration is defined. Okay? We, of course, are interested in instantaneous acceleration. Okay? Here's the average acceleration in the limit delta t going to 0. Okay? That is dv by dt, the time derivative of v with the time derivative of v, the velocity vector. Okay? Rate of change of v with respect to t. And so here's the x component of the acceleration, y component of the acceleration, z component of the acceleration. Yep. So acceleration is dvx by dt, dvy by dt. And as you saw a little while ago, this is the second time derivative of x. Okay. So there are the equations. And we've talked about this before, but let me remind you again. It's good to have pictures in your head, and those are easier to remember. Okay, are you accelerating? Okay. How's the velocity changing? I'm sorry? The magnitude is changing, okay? And if the magnitude is, if the final velocity is pointing in the same direction as the initial velocity, the magnitude is, the acceleration is pointing in the same direction as the velocity, okay? And the important thing is when the magnitude changes, the acceleration is tangent to the path you're traveling. Okay? So this is tangential acceleration. Let me give you another example of this. Again, only the magnitude of the velocity is changing, the direction is not changing, except that since the magnitude is decreasing, the acceleration is pointing in this direction, but it's still tangent to the path. Okay? So when your speed changes, your acceleration is tangent to the path. Okay. All right, so that's example 1, 2, and now we'll do example 3. Okay, so here the magnitude is not changing, only the direction is changing, and the acceleration in this case will point towards the center of the circle, and this is called centripetal acceleration. Okay, so this is called yeah, we'll call it centripetal acceleration. Okay, so I gave you two extreme examples, when only the magnitude is changing and when only the direction is changing. Of course, you can have a combination of the two, okay? So when only the direction changes, the velocity, the acceleration is perpendicular to the trajectory, okay? So the trajectory is in that direction and the acceleration is perpendicular to the trajectory. In this case, it's tangent to the trajectory, okay? So you got to remember that. And you will see that several times over the course of this and the next chapter. Yeah. All right, so here is the acceleration. Yeah. All right, now that we've talked about the general motion, we'll confine our attention to a two-dimensional motion, a special two-dimensional motion. Okay? This is called a projectile motion, and here's a projectile. So here's my keychain, and if you toss it like that, that keychain traveled in 2 dimensions, okay? And that was a projectile motion. Okay? So here is the projectile motion. Air resistance is negligible. Okay? We consider motion is under the influence of gravity alone, with the acceleration due to gravity being constant over the range of the motion. Okay, so what does that mean? So for this guy, the only force on this guy was the force of gravity. All other forces were negligible. And it moved in this range. G, the acceleration due to gravity was constant in that range. Okay. Is that a projectile motion? Yes. All right, let's say I throw this and it goes 100 kilometers up. Will that be a projectile motion? Gravity would change a little, and there, if I want to throw it 100 kilometers up, I'd have to throw it fairly fast, and then air resistance won't be negligible. Okay, that wouldn't be a projectile motion. Is this a projectile motion? No. Okay. So now you've seen examples of projectile motion and motion that is not projectile. Okay. All right, so, and this motion occurs in a plane, so all you need is x and y coordinates. So to describe this motion, I only need two functions. Okay. Now, so it turns out, like I said, this is a motion where gravity is the only force acting on it, okay? And so the acceleration vector is pointing like that. Okay, there's the acceleration vector. And with reference to this coordinate system, here's the x and y coordinate system, does this vector have an x coordinate? And does it have an x component? See that vector doesn't have an x component. A is 0I minus gj. What is g? 9.8 meters per second square on Earth. Okay. So there's the, okay. So AXI plus AYJ. That is the x component of the acceleration. That is the y component of the acceleration. What is the x component of the acceleration for this guy? I'm sorry? 0. What is the y component of the acceleration? Negative g. Okay? With reference to this coordinate system. All right, so let's do the following. You have seen this equation. When you're accelerating, okay, this is how your velocity changes. And let's write that equation for the x component. What does this say? The final velocity is initial velocity plus acceleration times time. So let's write the for the x component. X component is initial x component of the velocity, ax times t. What is the ax component of the acceleration? 0. So this guy is 0. So what is this equation saying? It is saying that for this projectile motion, the x component of the velocity is not changing. That's what that equation is telling you. And that's what this diagram shows you. See, there is the x component of the velocity, and that is not changing. Okay. Let's do the same thing for the y component. You guys following this? So your velocity changes only in the direction where you have acceleration. Okay. All right, let's do the y component of the acceleration. Y component of the velocity. Final y component of the velocity is initial y component of the velocity plus ay times t. Well, ay is not 0. So Vy is V naught y minus gt. Okay, again with reference to this coordinate system. Okay. And you see as time proceeds, y component of the velocity is changing. Okay, it's increasing in that direction. Okay, so there is the initial y component, and you see the acceleration is downwards, so it's decreasing initially and then increasing in that direction. Okay. All right, so let me ask you a trick question. So here's the projectile motion. I'm throwing this keychain, okay, and the parabola was pointing in this direction. What if gravity was pointing in that direction? Which way would it would, so if I throw it down, it would go up like that. Okay. If I throw it up, it will just keep going up. Okay. Did you guys understand? All right. All right. So now what we'll show you is, that this parabola, this trajectory is a parabola. Okay. And how would we show that? The y coordinate of this trajectory is a quadratic function of the x component of this trajectory. Okay. So you know that from your calculus classes that the graph of a quadratic function is a parabola. Okay. So if you are going on a projectile trajectory, as long as we show that the y coordinate and the x coordinate are related like that, then we know that this is a parabola. Okay? And we'll show that to you. All right, so let's do that. Again, in this coordinate system, the only force acting on this object is, what is the force acting on this object?
Gravity.
Gravity, the force of gravity. And so the acceleration is this vector, and it's 0I minus gj. Okay, so x component of the acceleration is 0. So x minus x naught is v naught xt plus 1/2 axt squared. These are the kinematic equations that you'd seen before, and we're applying it to the x component of the motion and the y component of the motion. What is this telling you? This is the x location, final x location at time t. What is x naught? The initial x location. What is v naught x? X component of the initial velocity and x component of the acceleration. This guy is 0. Okay. We start off at the origin. So this guy is 0. Initial x component of the velocity. That is the initial x component of the velocity. That is v naught cosine theta. Okay, so what is this equation telling you? At t equal to 0, when the object was at origin, at the origin, and it was launched with an initial velocity of v naught, initial speed of v naught at an angle theta naught. And this is giving you its x coordinate at any time. It's giving you the x coordinate as the projectile is moving. And that's what this is. Okay. So I'm going to erase that. And now let's look at the y coordinate of the motion. Y component of the motion. Y minus y naught equal to v naught y t plus 1/2 ay t squared. Okay, again, we are starting at the origin. So this guy is 0. V naught y is the initial y component of the velocity, which is v naught sine theta naught. So y is v naught sine theta naught t plus ay. What is ay? Very good, negative g. What is it that you're trying to do?
Determine y given value of x for
Yeah.
time.
So you're trying to prove that this is a parabola. What you're trying to do is you're saying that the y coordinate of this trajectory is a quadratic function of the x coordinate. All right, so here's what we'll do. From this equation, you have t equal to x over v naught cosine theta naught. So we're going to substitute that here. So y equal to v naught sine theta naught, and for t we'll write x v naught cosine theta naught minus 1/2 g x squared v naught squared cosine squared theta naught. There it is. Y is a quadratic function of x. Okay, so this is the cleaned up version. Y is a quadratic function of x. Okay. And since this guy is negative, remember from your calculus classes, when a is less than 0, the parabola points downwards. Okay. Let's see, your a is negative. Okay, all these inside the parentheses are positive quantities, and you have a negative there. All right. So what we have shown to you is the following. The trajectory of this guy is not a parabola. The trajectory of this guy is a parabola. Why is the trajectory of this guy not a parabola?
You have to account for air resistance.
So this fellow, acceleration is not constant. Okay? You get a parabolic trajectory when the acceleration is constant. Okay? So that's what we showed now. All right, there'll be a couple of things we'll be interested in. We want the range of the projectile, okay, because we want to be able to hit ships and stuff like that from far off with cannons. Okay. The range is the horizontal distance the projectile travels when it comes back to the same height. Okay, that's the range. And the range is given by V naught square, that is the initial speed square, times sine 2 theta naught. Theta naught is the launch angle. Sine 2 theta naught divided by G. G is the acceleration due to gravity. Okay. On the moon, the acceleration due to gravity is about 1/6 that on Earth. So on the moon, if you throw an object at the same speed at the same angle, it'll go 6 times further. Okay. So that's the range formula. And this is the maximum height. So that's the maximum height it rises above the point which you've thrown. Again, that's the initial speed, sine square of the initial launch angle divided by 2g. When do you get the maximum range for a given speed? At what angle do you need to throw to get maximum range?
45 degrees.
45 degrees. See, the max for a given speed, if theta is the only thing you're changing, the maximum value this can take is 1, and that happens at sine of 90, which makes that 45 degrees. Okay? So you get maximum range for 45 degrees. Now here's something most people don't know, but complementary angles give you the same range. See, 15 degrees and 75 degrees will give you the same range. 30 and 60 degrees give you the same range. What is the complement of 45?
45.
45. 45 and 45 give the same range. Yeah. Okay, so here is a parabolic trajectory. Here is a parabolic trajectory. This is the trajectory of a real baseball or a tennis ball, let's say. What can you say looking at that picture? So when will you have a parabolic trajectory? When only gravity acts on it. This is not a parabolic trajectory, so there must be other forces acting on it. And in most sports, if you put, so in tennis, if you put a top spin, okay, the air, there's something called the Magnus effect. Okay, so you learned this in chapter 14. So if a tennis ball is going like that, and if you give it a top spin, what it does is it drags the air like that. This air is traveling faster than, so okay, if the ball is given a spin, this air is traveling faster than this air, and the pressure here is lower, and so there is a net force in this direction. Okay, so there's the force of gravity and this force due to the spin of the ball. Okay? And so you see, instead of traveling like that, because of the additional force, it falls faster. Okay, but now that you've learned that when does projectile motion occur? When only gravity acts. And so if you have a motion where it's not going on a parabolic trajectory, you know right away that there's some other forces acting on the object. Okay, now we'll look at uniform circular motion. What do you think that says? What is that saying?
Constant velocity in a circle.
So, yeah, it's a circular motion, and when we say uniform, what we are meaning is the speed is constant. Okay. Is anything changing about the velocity?
Yes, the direction.
The direction is changing. So if you're going in a circle, even if you're going at constant speed, so, I mean, this is drawn there and it's showing. So your direction is changing. We mentioned this a while ago. If only the direction of your velocity changes, what direction is your acceleration? Well, you're accelerating because the velocity is changing. What is the direction of your acceleration? It's perpendicular to the trajectory. Okay? So, yeah, you're right. It is pointing towards the center. It's perpendicular to the trajectory. When only the speed changes, then the acceleration is tangential to the trajectory. Okay? So when only direction changes, the acceleration is perpendicular to the trajectory, and it is pointing towards the center, and that's why it's called centripetal acceleration. Okay. The magnitude of the acceleration, we'll show you the proof in a second. The magnitude of the acceleration, see, the direction of the acceleration is also changing, so the acceleration is not constant, but the magnitude of the acceleration turns out to be constant. Okay? The magnitude of the acceleration is the speed square divided by r. And you guys probably have experienced this. At the same speed, it's harder to go in a smaller circle. If you go in a smaller circle, the acceleration is greater. You'd better have sticky tires. Okay? And if your tires are not sticky, what will your car do? It'll go in a bigger circle. Okay? It'll go in its own circle. It won't listen to you. Okay? All right. Now, I'm just going to start you guys on the proof. I'm not going to go over all the details. Okay. So here's the deal. We're going in a circle. We're going at constant speed, so the magnitude of the velocity is not changing. So let's say there's your location. Okay. So at this point, okay, there you are. You're making an angle theta with the x-axis, and it turns out this angle is equal to that angle. Okay. So we're going to write the velocity in terms of its x and y component. Okay. The x component of the velocity is v sine theta. Okay. So the velocity is v sine theta, and I, and it's in the negative direction, so negative v sine theta. Plus, can somebody help me out with the y component of the velocity? There's the y component of the velocity. Very good. Who said that? Okay, v cosine theta j. All right, well, what is sine theta? Well, let's look at this triangle. Sine theta is y divided by r. And what is cosine theta? X divided by r. All right, there's the velocity of the gut. Now, if we want the acceleration, we'll take the time derivative of that. Okay, so to get the acceleration, all you have to do is, okay, let's see what all is changing here. Is v changing? V is the speed. That's just the magnitude. Is v changing? No. Is r changing? R is the radius of the circle. No, that's not changing. Is y changing? Y is changing. As you're going around, the y coordinate is changing. And x is changing. Okay? So is equal to minus v over r dy by dt I plus v over r dx by dt j. What is dx by dt? That's the x coordinate of the car changing with respect to time. That's his x component of the velocity. This is his y component of the velocity. Okay, and that's what's written here, all of that. Okay, and then Vy was this guy. You can substitute that. Vx was this guy. There you have it. There is the x component of the acceleration, y component of the acceleration. If you calculate the magnitude of the acceleration, you get that. The magnitude of the acceleration turns out to be constant. It's equal to v squared over r. All right, so this is important. Okay, we haven't talked about this, but you guys all know this. You guys have. What is Newton's second law? I'm sorry?
Sorry.
Okay, go ahead, think loudly. You all know it. You're not saying it. F equal to ma. That's Newton's second law. What is Mr. Newton saying? If you are accelerating, if that's your acceleration, that's the force acting on you. That's what Newton is saying. All right, now, so here the Earth. Here the International Space Station going around the Earth. The International Space Station is going at 8 kilometers a second. Okay, it goes from here to Ormond Beach in a second. Its speed is not changing. Is it accelerating?
Yes,
Why is it accelerating?
due to the force of gravity perpendicular to the space station.
Why is it accelerating? Because the direction of its velocity is changing. Its speed is not changing. It is accelerating. There must be some force acting on it. Okay, and our friend here was answering 3 steps ahead. You know, I wanted him to take 1 step at a time, but okay. So that's okay. So anytime an object is accelerating, now you just go for looking for the force that is giving you that acceleration. Okay. All right. So you will end up seeing this everywhere. Okay. So there is the magnitude of the acceleration, and there's the magnitude of the acceleration, and this here proves that the direction of the acceleration is pointing toward the center. You see, when theta is acute, the x and y component of the acceleration are negative, so the acceleration is a vector pointing in the 3rd quadrant, and so it's pointing in toward the x, toward the center, and that's what this thing proves. All right. When your speed changes, are you accelerating?
Yes.
Okay. What direction is the acceleration?
Tangent.
Very good. Tangent to the trajectory. When your direction changes for the velocity, are you accelerating?
Yes.
Yes. What direction is the acceleration? Perpendicular to the trajectory. Okay. So we saw that. Try and remember that. So when the speed changes, acceleration is tangential to the trajectory. When your speed changes, acceleration is tangential to the trajectory. When the direction changes, acceleration is perpendicular to the trajectory. Okay? And in which direction is it perpendicular? It's pointing towards the center of the circle. All right? So we're going to remember that and apply this to a curved road. So let's say you're driving on this road, and let's say you're speeding up. If you're speeding up, if your speed is increasing, you have a tangential acceleration. Okay? And if the road is curving, you have a centripetal acceleration. Okay? So there's your total acceleration. What if at this point you're slowing down? Your tangential acceleration will be in that direction. You still have that centripetal acceleration, and your total acceleration will be like that. How about when you're in a straightaway?
It's only tangential.
Very good, very good. You don't have a centripetal acceleration, okay? So only when you're on a curved road, you will have centripetal acceleration, okay? And on a straightaway, all you'll have is tangential acceleration. Okay. All right. All right, now let's do the following. Okay, so this is a parabolic trajectory, right? I toss this thing. Now let's get on a skateboard, and I skate at constant velocity. And I throw this object. What will its trajectory be? That's the question we'll answer.
Well, it would be the same plus the horizontal x velocity of the skateboard.
So for a parabolic trajectory, what you needed was a constant acceleration. You're on a skateboard, the acceleration is not changing. Okay? If you're going at a constant velocity. It will be parabolic as well. So if you're going in this direction and tossing it in the same direction, the parabola will be wider. That's all. Okay? From your perspective. Okay? So that's what we want to do. Did you guys understand that? Okay. All right, so in physics we give special names to that. If two frames of references are moving with constant velocity with respect to each other, okay, and one is an inertial frame, that other is an inertial frame as well. All that it means is F equal to ma works in both the frames of reference. The laws of physics are the same in both the frames of reference, okay? All right, we won't get into all that. Okay, so let's say here's one observer. We'll ignore one of these cars. Here's another observer. Okay, and so in similar to that example that I talked about of the skateboarder, let's say this dog is juggling a ball. The ball goes on a parabolic trajectory. What does this person see? They see a wider parabola. Okay. So when the ball is thrown in this direction, you see a wider parabola. When the ball is thrown in this direction, you see a narrower parabola. Okay. Did you guys understand that? Okay. All right. So this is the moving frame. So here is that frame of reference attached to the car that is moving, okay? So in this, and the car is moving at steady velocity, so with respect to this person, according to this, the car is moving in that direction, okay? So this is the frame of reference of the person. There is the ball at this instant. Okay. There is the position of the ball in the car frame of reference. There's the position of the ball from this person's frame of reference. Okay. All right. So now you can see that. So here's the notation. The position of the particle with reference to frame S. The position of the particle with reference to frame S prime. And this thing is the position of S prime with reference to S. That's the notation. Okay. And you can see that this vector plus this vector is equal to this vector. I will show you an easy way to remember this. So the position of the particle with reference to frame S is equal to the position of the particle with reference to S prime plus the position of S prime with reference to S. Okay, here's how you remember. It's simple. Position of particle with reference to S. All I did was inserted S prime in between. Okay. So, a new reference frame can be introduced in between. Now here's an equation, and you've learned that if you hit this guy with a hammer, you got to hit these guys with a hammer. Take the time derivative of that, you'll have to take the time derivative of this. Okay? So you can take the time derivative of that. You do the same thing here. What do time derivatives with of position do?
Generates velocity.
The velocity. Okay. So this is the velocity of the particle as seen by this person, and that's the velocity as seen by that person. Okay. And so on. That's the velocity of this frame with reference to that frame. Okay. So anyway, you go through all of that. Velocity of the particle in frame reference A. So here we call it A and B. Velocity of particle in frame reference A, velocity in reference B, and velocity of reference of frame B with respect to A. There's the velocity, that's how they add up, and again this notation is the same. PA, all you did was inserted B in between PA. Okay, that's how you remember it. Then you take the velocity of time derivative of the velocity. If the frame is moving at constant velocity, then this will be 0. And what this is saying is the acceleration in frame A is the same as acceleration in frame B. The acceleration seen by this person is the same as acceleration seen by that person. You'll get a parabola. Okay? So gravity will be the same in both frames of reference. Okay. That's what it's saying. All right, so this is what we'll be interested in. So really, in a lot of our problems, this is the only formula we'll use. Okay. And what this formula says is velocity of an object in frame A is equal to velocity of the object in frame B plus velocity of frame B with reference to A. Okay. So for instance, let's say it's raining straight down. When you're standing on the ground, that's what it appears. If it's raining straight down, how will the rain appear to you driving in a car?
Be the negative velocity of the car.
Okay, so let's see. Rain, no. Velocity of the rain with reference to car. That's what we're interested in. Okay? We just saw that velocity of rain with reference to ground plus velocity of ground with reference to car. Okay. Now, velocity of car with reference to ground is like that. And the ground with reference to car is going in the opposite direction. Okay, so velocity of rain with reference to ground. Oh, is that, okay, so velocity of rain with reference to car is velocity of grain with reference to ground minus velocity of car with reference to ground. So minus of that, so this plus this. And you intuitively knew this, so that's how the rain will appear to you. Okay, so this will be the velocity of rain with reference to car. Okay. All right, that finishes this chapter. Okay, so that's how the rain will appear to you in the car. Okay, so we will stop.